Hi, welcome to Engineering Q Vectors. Today we're going to talk about Q division. In the previous installments, we explored Q-Algebra multiplication, what we're going to call Q multiplication for short. And this supersedes classical vector products for all the reasons stated previously. Now we're going to explore Q division, and we're also going to include an introduction to the Q-Algebra syntax. So going back to the previous videos, we demonstrated that in order to come up with a division, that we had to multiply the top and bottom by C, which left C as a scalar, and that division could be done with a triple multiply. Well, right now we're going to show that this works out to be true. We're going to substitute C now with A, and then we're going to work through the algebra. So this is the AB matrix with the vector A multiplied, and we're going to multiply through. And we end up with this. I'm going to carry this down to the next slide. And now if you notice here, we have minus AX, BY, AY. This is AX, BY, AY. So this cancels with this. And this guy, which is AY, BX, AX, AY, AX, BX, this cancels with this. And so you bring the other terms down, you end up with this. And then what you can do is factor out the BX here and the BY here. All right, and that leaves what looks like the dot products here. So this denominator, and this, by the way, is the definition of A squared. It's just the dot product of A dot A, because the cross components cancel. And so this would be, this is this. And then this cancels with part we factored out here, and therefore you're left with bx, by, which is the original components of vector b. They're showing you that the vector division actually works. Now, on the other hand, if we substituted b to divide by b instead of dividing by a, we end up with a mess which turns out to be the reflection of a about b. So how do we divide by b? This means that division, like multiplication, is left and right sensitive. Okay, and the solution is to dividing by b is to divide b from the other side. So in other words, if you left multiply b and then divide b, in other words, you left multiply both sides by b. In the previous example, we right multiplied. Okay, then you end up with the right answer. You get a out. So now, because multiplication division can be either done from the left or right, we need to develop a way of unambiguously expressing it. And so, since we now put the AB matrix in brackets to show it's a matrix, we can show division from the right by showing B with a bracket. And the reason for this bracket, okay, well, I'll show you the reason for the bracket on the next page. Okay, and this ends up, division on the right by B turns out to be left multiplication on both sides by B. And left division by A is the right multiplication by A on this side. So essentially, a right divide is really a left multiply when you work it all out, and a left divide is really a right multiply when you work it out. And so this is the notation. When you right multiply the matrix by C, you can put the bracket there the bracket's redundant because you already know it's a right multiply. But in the case where you've got using the horizontal bracket here, you need a way to say if the divide is left or right. And therefore, this right divide by C can be expressed using the horizontal bracket like this, using the bracket here, using this bracket to delineate that that's a right divide. Okay? And a left divide, the bracket goes on the other side. And now, for A divided by B, straight out, now this is not the matrix divide, this is the actual vector divided by the vector. We simply roll the B underneath, and we maintain the brackets for which one's left and which one's right. So the brackets are more important when you do division, and you have the horizontal division sign, because the horizontal division sign is left-right ambiguous. Now, you don't have to worry about if you're dividing and you're dividing by, let's say, an a squared, because that becomes a scalar, and scalars are left-right. Doesn't matter which way you divide them by. So now what we said before is by right dividing by c, that's the same as this, and that is resolved. The way you can look at how you resolve it, if you've got to complete the matrix in the denominator. In order to complete the right divide, you have to left multiply top and bottom. This now completes the matrix in the denominator. That's the way, the key, how do you look at it? This works out to be c squared, and then you're left with c, left multiplied c times ab. Okay, and the same thing works out for c divided from the left. Now, because we can say that a right divide works out to a left multiply divided by c squared, we can do the same thing with the plane vector here. Again, we want to complete the matrix in the denominator. If this is a right divide, we want to left multiply top and bottom. Oh, and the reason why there's no horizontal bar here, because that would imply that these are divided before they're multiplied, which wouldn't help you. So this is what we're not multiplying by 1, okay? What we're doing is we're multiplying the top and the bottom by the same amount. So we change the top and bottom equally, which is effectively multiplying by 1. But you can't show the divide symbol here, because then what you're saying is you need to divide these before you multiply. And in Q-Algebra, the order in which you do stuff is critical. Okay, so there's no divide symbol there. Again, coming back to a divided by b, right divided by b, in order to complete the matrix in the denominator, you multiply the denominator by left b, and you left multiply the numerator. Now, an interesting thing happens. Because these brackets are closed around this operator, the minute you switch this guy to be multiplied by this guy is no longer attached to this guy. Okay, that's why over here the bracket disappears. Now that you're left multiplying a free a, then you can add the bracket to show that this a is now attached to that b. So the problem is, so there's a little problem with brackets here, because the brackets, there should be one operator per bracket. But in the case of the basic matrix, there's one operator for a pair. So these really should show like half brackets here, but I don't have a symbol for half brackets. So you just have to bear with the fact that once you close this guy with another, okay, it frees up the bracket that these guys shared, and he becomes free, such that when he is left multiplied by b, he is now part of this AB matrix, or BA matrix in this case. And the same thing works for left divide by b. Now everything I'm showing you from here is valid in 2- and 3-dimensional space. There's something strange in 4-dimensional space I'm still exploring right now. And the idea of how you work that out, we're going to explain that in the next video when we get into the rule sets and where they apply and where they don't apply. But right now, this is valid for stuff we're doing in Ethereal Mechanics, because right now in Ethereal Mechanics, we're sticking to 3-dimensional space. So, but again, that'll be explained more in the next video. And here's a new Pythagorean theorem retraction. Thanks to Walter for reminding me of the law of cosines. I totally forgot about that. I haven't used that in like 25 years maybe. So there is a thing out there called the law of cosines, which is this. It's a non-vector equation. It's just a magnitude equation. And from the last video, or 2 videos back, we developed the law of cosines, which I called the new Pythagorean theorem, which it isn't. It's the law of cosines. I derived it using Q-Algebra, and it was a very simple derivation. Okay, if you look at the proofs on Wikipedia for the law of cosines, all the other techniques they use is very difficult. Well, not difficult, but they're a little more involved, let's say it that way. The Q-algebraic derivation was like 2 lines. It was very simple. It was actually mindless. But now, for the people to understand that this dot product here works out to be the magnitude of A times the magnitude of B of cosine of the angle AB. And you might be wondering why the signs here are different between the law of cosines as it's published and the Q-Algebra version of the law of cosines. And the reason for that is because this derivation up here uses this angle here, whereas the dot product of AB uses this angle here. And the cosine of this angle is the negative of the cosine of this angle. So this is the same equation. It's just where you define this angle AB from. And the dot product, it defines it here. And the way the derivations on Wikipedia for the law of cosines, it's this angle on this side. Okay, so essentially, this is good because it shows Q-Algebra does agree with law of cosines, which is in the Wikipedia article is proven so many different ways. It's insane. But now we have another proof for the law of cosines, which is actually it's a reflection that Q-Algebra actually works. Now let's take an example application of Q-Algebra. And we're going to take the Q-vector function here. If you remember this is back in the earlier, this is from Ethereal Mechanics. But now we're going to express it as a pure vector function, the left divide of the velocity of the source by the vector r. And we're going to find the derivative of the velocity of r as of s as the acceleration of s. And r is the position vector from the target minus the position vector of the source. And therefore, the derivative of r is the velocity of the target minus the velocity of the source. These are things we know from before, but now we're doing it completely as a vector equation. Whereas the derivation we did before was a mix between vector and standard. So what we have here is we have two functions of time, and then we have to choose the chain. We're going to take the derivative of this function. We're going to use the chain rule, which says we take the derivative of the first divided by the second, multiplied by the second, which would be divide, minus the first times the derivative of the second. Now this, I'm going to show you the derivation of this on the next page. So to show you that this is the correct outcome. There's another Q-algebra expression we're going to use. Now if we propagate all the signs through and we replace r with the derivative of r with vt minus vs, and then we work out all the signs, we end up down here, which is really, really interesting. By multiplying by the direction vector on the right, we end up, and we multiply on the left by km qt, we end up with all of the new electromagnetism in one equation. The problem, this would be Coulomb's model, this is new induction, and this is the magnetic effects. Plus, there's a little bit more in here that is not, that we don't have accounting for, that we have to do experiments to find. The problem is it comes out in Q space. So that's why I'm going crazy finding out what Q space really means to see if we can actually measure something in Q space. So, but other than that, now there's one problem with this model. These signs are backwards. That's where I'm having the biggest trouble. And the reason why these are backwards is because this derivative has a negative sign. Okay, now this might actually be the truth. It might be that this is the true. Remember I said in many videos before that what we see at one echelon may look nothing like the lower echelon. Okay, we're trying to use the pretonic models to derive the electronic echelon, or new electromagnetism, which would be. This is the pretonic echelon. It might very well be that depending on how the pretons spin around in the structure of the electron, that they can synthesize these with the right signs at the upper level. That's why we need a better model. That's why we still need to develop the pretonic electron model, because it might just very well be that this is the correct model of what happens at the pretonic level, and how the pretons behave actually synthesize what we see at the electronic level, where these signs are reversed. And maybe that extra little part that's in here actually doesn't present itself at the electronic level. Okay, so this is very exciting, very exciting. This is blowing my mind. And now that I have more time, for the reasons discussed in the behind the scenes, I'm going to take a very thorough look at that. So we may slow things down because I need to go down to the 4 dimensions to see what the deal is. There's things about Q space that I don't know all the details about yet. I can do everything in 3 dimensions, but at 4 dimensions, there's something else going on that I'm still trying to put my finger on. Anyway, going back, we're going to derive what the derivative of this guy is, the second part of this, by saying that we're going to take the derivative of some constant function of t, which doesn't, that's a little asterisk, is just a placeholder, right divided by r. This could be a vector, this could be a matrix, doesn't matter. We're right dividing by r. So what we're going to do is we're going to use the standard thing you did when you first learned calculus, derivative calculus, we're going to take the function of r plus r delta t minus the function at r divided by delta t. That's your standard, and you take the limit as delta t goes to 0. This is the thing you learned in college calculus or even high school honors calculus. This is the basic idea, one of the different forms of integrating. All right, so what we're going to do now is we're going to take r plus, this is derivative of r times delta t. Okay, since r is in the denominator, we're going to replace this r with r plus r dot delta t minus the normal function divided by delta t. Okay, the first thing we're going to do with this is we're going to multiply the top and the bottom by these equations, okay, which is going to work out to this. And then what we're going to do is multiply the top and the bottom by just multiply by r. And that's going to work out to this. And then what we're going to do is we're going to propagate these multiplications through the parentheses. We end up with this. This guy cancels with this guy. And then we're going to divide a delta t out from everybody, which leaves this. And then when we take the limit as delta t goes to 0, this goes canceled out. And that's what we're left with. And that's what we put back into this other equation here, where we put vs r dot over r squared. And that's where the minus sign is definitely there. And this is good because when you look at your standard calculus tables, they say that if you have a function of time that's of the value, the derivative of this is n times u to the n minus 1 times the derivative of u, which is exactly what this works out to be. That's from your standard calculus derivative tables. So let me give you a little recap. We demonstrated Q division with some identities. We demonstrated the application of Q-Algebra to current work in Ethereal Mechanics. And now with proper vector division, Q-Algebra can now be applied to everything that was once the domain of classical algebra, geometry, trigonometry, and calculus. Okay, so thank you for your donations. There's people actually giving me, I didn't know you could do this. You can go on to my website at distinti.com. There's a donate button. You can actually sign up for a monthly installment. That's pretty cool. I thank you people that are doing that. Please give me thumbs up wherever you can. Somehow that helps me. I don't know how. And thank you.